Hello, everyone, and welcome to another webinar of RS3. Before I start the webinar, I just wanted to let you know that the webinar will be recorded and it will be available in our YouTube channel within a week. Also, during the webinar, if you have any question, feel free to type your question, and at the middle and also at the end of the webinar, we will try to get back to your question. If we didn't have enough time, we will answer you through the email that you register for this webinar. So without further ado, let's start and talking about the recent feature that we developed in RS3, which is hybrid mesh. So today we want to know why we implemented hybrid mesh in RS3, what it does, and when we have to use it. My name is Sina Moallemi. I am the product manager of RS3, and today with me I have Dr. Amir Jameei, who is going to help me during the webinar, and we'll cover the theory background behind the hybrid mesh. In case you are not familiar with Rock Science, let me introduce briefly the company. So Rock Science is a world leader in developing innovative 2D and 3D softwares in civil and mining application. From a team of 25 years ago, the team has grown, and now we are over 80 employees. And the number of our customers are now over 10,000 users all around the world. Here you can see the full list of our 19 products that we have, which are all tailored to meet all your civil and mining and geotechnical needs. One of the main features of using Rock Science products is that they can communicate with each other. So for example, if you have a model in slide 3, you can easily import it to RS3. So you don't need to recreate the geometry. You don't need to go and redefine the material properties. All of them will be imported to RS3, so it can save a lot of time for yourself. Here you can see the ecosystem of the Rock Science softwares and how they can communicate and talk to each other. But today we are going to focus on RS3. So let's review the agenda for today. At the beginning, I'm going to introduce RS3 to you very briefly, like the workflow of model creation, how it works. Then I explain different element types that we have in the program, what is the advantage and disadvantage of each of them. Then the main topic of today, hybrid mesh. What was the idea behind it, why we implemented it, and how to define it in RS3. And then Arsalan will join me to talk about the theory behind the hybrid mesh, and then we conclude the webinar by going over to demos. The first one is focusing on hybrid mesh, application of hybrid mesh in slope stability analysis, and the last one is the application of that in tunnel. RS3 is our 3D general finite element package, which has a wide range of application in mining and civil. So in mining, I can mention you can do a slope stability, you can do large scale mines, modeling large scale mines, you can do sequential underground excavation. Last year, we introduced a feature called DFN, discrete fracture network. So if you have a densely jointed rock mass, you can simply, with just few clicks, define this joint distribution and assign it to your model. For civil application, you can do consolidation, seepage analysis, dynamic analysis. With the tunnel designer that we have in RS3, you can model sequential tunnel excavation, apply the support around the tunnel, like bolts, like liner, and the list keeps going on. I'm not going through all of them, just a brief introduction for you guys. In order to create a model in RS3, you need to follow these steps. The first step is geometry creation. So you can either use the primitive objects that we already have in RS3 to create your geometry, or if you have the file, let's say you have an OBJ file, DXF file of your geometry, you can import it to the program. We have an advanced repair tool. So whenever you are importing the geometry, it's going to find if there is any defects with your with the imported geometry, and it can fix it for you and repair it for you. Next step is material assignment. So in RS2 and also RS3, we have a comprehensive material library for both soil and rock, like Moore Coulomb, generalized Hook-Brown, modified calculate softening, hardening models, that you can use them to describe what exactly you have in your site. Also, we have borehole manager that you can define the thickness of each layer, and just by defining the location of the boreholes, we can create the whole geometry for you. Next step is divide all, which is a 3D Boolean operation. So what it does, imagine you are importing lots of volumes and different surfaces, as you can see in this image. After you do the divide all, it finds all the intersections between them, and then you can end up with a clean, like open bit, similar to the image that is shown here. The next step is applying load and boundary condition. Depending on the type of analysis you have, you need to assign different load and boundary condition. For example, if you are doing just solid analysis, we have different real strength conditions. If you are doing seepage analysis, you can apply, let's say, total head, infiltration, or seepage phases as well. If you are doing dynamic analysis, you can apply different dynamic boundary conditions, such as absorb boundary condition, free field to your model, and do your analysis. Next is meshing. So you need to discretize your geometry in order to be able to solve it with finite elements. Currently in RS3, we have 4-noded and 10-noded tetrahedral elements. And also in the last release, we added another option, which is called hybrid mesh, that we are going to cover today, which mix both these 4-noded and 10-noded together at the same time. After you created the mesh, you can just go and compute your model. You can do SSR analysis to find the stability of your slope, for example. You can do coupled, uncoupled, solid fluid analysis, dynamic simulation. You can find the natural frequency as well. And finally, you can go to the result tab and see the results on the external boundary around the excavation, or if you have a region of interest, you can define it and define the contour plane and see the variation of the results in the defined area. Okay, having that said, getting introduced briefly with RS3, now let's jump into the main topic of today, which is hybrid mesh. As I mentioned, in RS3, we have either 4-noded tetrahedral elements or 10-noded. 4-noded, we call them, they are linear elements. Why? Because the displacement is interpolated linearly inside of the elements. So the derivative of displacement, which represents the strain, would be constant because displacement is linear inside of the element. So you can imagine that using these elements at the areas that we are having a strain concentration or higher displacement gradient is not a great idea. On the other hand, 10-noded elements, they are higher order. So the displacement will be interpolated non-linearly. Therefore, the strain is not constant, so they are a better candidate to be used in the areas we have more displacement gradient. To understand the difference between these two, let's go to a very basic example. Imagine we have a higher order solution and we want to interpolate that using linear elements and quadratic elements. So linear elements, they only need two nodes. Let's say they are located at x1 and x2. And because displacement is interpolated linearly between these two, you can see it can create a very large error. And the results are not close at all to the actual solution. But when you use quadratic elements, we are introducing the third node, x3, which is located between x1 and x2, and displacement is not interpolated linearly anymore. So the results can be matched better with the actual solution. If you want to use linear elements and get a more accurate results, you need to increase the discretization. You need to define more of these linear elements. So as you can see here, the error would be reduced by increasing the number of elements, number of linear elements in your model. Now let's see the difference between these two elements in action. So here I have this example. It's a circular excavation in an elastic infinite domain. I picked this example because we already have the analytical solution for that. So here we have P1 and P2, which are the field stresses applied to the model. For this case, I'm applying 10 megapascal in each direction. And I have the distribution of radial and tangential stresses. Because the tunnel face is basically a free surface, so I expect to get the radial stress right on the boundary to be equal to 0. So what I did here, I ran it first with a 4-noded element with the discretization that is shown in this image. I have 55,000 elements. And I measure the radial and tangential stresses, and I compare them with the analytical solution. As you can see, when I'm closer to the surface of the tunnel, the error is very high, especially for radial stresses. I expect to get the value of 0, but what I'm getting is about 4.5 megapascal. So it's not good. However, when I'm further from the tunnel face, the results are close because the displacement gradient is not much. Now let's repeat the same analysis, this time only with higher order elements. So I'm going to keep the same number of elements, only element type is changed to be 10-noded. And you can see the results are almost matched with the analytical results. This is the power of higher order elements. Now let's move this example one step ahead and see the effect of mesh discretization to the results. So I introduced two additional cases. First case, the number of elements is 145,000, and the second one is 350. So let's see the results. This is the first one we already discussed. The second one, when I increase the mesh density, I expect the results get closer to the analytical solution, which is happening. And if I make it even more denser, the results getting again closer, but it's not still close enough to the analytical solution. Just compare what we have with the results of the 10-noded that we got from a coarse mesh. So this shows even if you have a coarse mesh and use a higher order element, you can get very accurate results. But if you reduce the mesh discretization of a linear elements, it still takes a lot of time. You need to keep reduce the mesh size a lot in order to capture the same result. Let's summarize what we just talked about. So let's see the advantages and disadvantages of each of these two element types. 4-noded, because you are introducing less nodes and therefore less degrees of freedom to the model, the size of the matrices are smaller, so the speed of calculation is faster. But the accuracy of the result is not great. On the other hand, 10-noded, we are getting very accurate results, but because we are introducing more nodes and more degrees of freedom, the size of matrices are huge. Therefore, we need more computational. We need to the calculation time would be a little bit slower. Besides these two differences, there is one more fact that we have to consider, and that's the limitation of the hardware, because it can affect the type of solver that is used in your analysis. Let me elaborate on that a little bit more. So in RS3, we have direct and iterative solver. Direct solver uses LU decomposition, which requires a lot of memory. But for the typical models that we are solving, like less than 1.5 million elements, the speed of solving is way faster than iterative solver. The iterative solver requires less memory, but it is a little bit slower in comparison with the direct one. So when you assign a 10-noded element to your model, because it is taking a lot of memory to create the matrices, you may not have enough memory available on your computer to use the direct solver. So your solver can be changed to iterative, and it reduces the speed of calculation. This is one of the most common questions that I'm getting from our customers, that they say, why whenever I'm switching the element type from 4-noded to 10-noded, the speed can reduce significantly. This is the reason, because we didn't have enough available memory and we are using iterative solver instead of direct. This limitation was the main idea that we developed hybrid mesh. So why we have to use these higher order elements everywhere for the whole domain? We only need these elements at the areas that we have higher strain concentration. As we saw earlier, when we are far from these areas, the results of 4-noded are very good. So if we be able to define regions and tell the program to keep 10-noded elements inside of them and assign linear elements for the rest of it, we can solve the problem that I mentioned earlier, because we can save a lot of memory. We are reducing the amount of degrees of freedom significantly, and we can do the calculation much faster. This is the benefit of having hybrid mesh. Here you can see what's happening in the mesh. So currently, if you assign higher order elements everywhere, so all the elements would be higher order. But now we are asking you to define a region you would like to have higher order zone. So we keep them as like 6-noded or 10-noded in 3D, and the rest of the elements would be linear. So this is what is happening for hybrid mesh. If you like to define it in RS3, you need to follow 2 steps. In step 1, you need to go to mesh, define higher order region. So you need to define the location and also the size of the box in the area that you are interested. If you have already selected a volume and then go to mesh, define higher order region, that volume would be your higher order zone. Very similar to SSR region that we had earlier. A second step, you need to change the element type. So now we have a third option, which is a mix of 4 and 10-noded elements. And then you just go click mesh, and the program will take care of the rest of the calculation. If you want to know how the engine is handling the calculation, that's the next chapter of this webinar that Dr. Amir Jameei is going to present. So give us a second to switch the presenter, and we will continue from there.
Thank you, Dr. Moallemi. I appreciate it. Hello, everyone. I hope you're doing well. In the next few slides, I'm going to briefly talk about the theory behind the hybrid mesh implementation in RS3. Well, all finite element meshes must be compatible, meaning that they must ensure continuity of the solution across all the edges and surfaces that are shared between elements. For example, these 3 nodes are located at this edge that is shared between these 2 elements. And the displacement, if it is the deformable solid, the displacement must be continuous. We have the same concept on all the other elements, and this applies to every other edges. When we have continuity of the solution, the deformed configuration will be compatible, meaning that deformed configuration of those edges comply with the deformation of the elements around them. However, when combining 2 types of mesh with different orders, we have some challenges. As Sina mentioned, we have a zone which we call it the hybrid zone. Inside this zone, we have higher order elements, and outside of the zone, we have lower order elements. At the boundary of higher order and lower order elements, we have some challenges, because there are some mid nodes that are located here, but they're part of the higher order and not part of the lower order. For example, if you take a look at this mid node, this is part of the green element, which is a high order, but it's not part of the blue element, which is our linear element. When we have such a problem, then the deformed configuration may leads to a gap or even overlap, which means that our mesh wasn't compatible and the solution is wrong. There are some ways to solve this issue. I'm going to read them. The first approach is using elements with augmented nodes. In this approach, the blue element is no longer a linear one. It has 4 nodes instead of 3, and it's a special element that their shape functions can be mathematically obtained and then used in our finite element method in the discretization in assembling the matrices and vectors, and we can solve the problem without any error, and it ensures that solution is continuous and also the mesh configuration is compatible. The second and third approaches are penalty and Lagrange multiplier approach, and the last approach is the master-slave elimination. Master-slave elimination is an approach that treats the mid edge, that treats the shared edge as an edge which has nodes that we designate them as slave and master nodes. The slave nodes are located in the middle of the edge, and the master nodes are located at the corner of them. By imposing a constraint equation that describes and defines behavior of a slave nodes based on the behavior of master nodes, we can eliminate it from the system of equations, but we still have its effect embedded in our system of equation. So finally, it will result in a reduced system of equation, which ensures continuity of deformation or solution, and our mesh is compatible, our result is correct. This method is very elegant, accurate, and also flexible for use with any type of elements like 3D, solid, joints, linear, structural, and etc. This method is implemented in RS3. Let's take a look at the one-dimensional bar element in which we have 7 degrees of freedom, 7 nodes, 7 displacement, and 7 forces, actually. The original system of equation is the one that we know KU equals F. If we assume node 5 as the slave node and the other nodes like node 4 and 6 as master ones, and if we describe the constraint equation as of U5 is equal to average of U4 and U6, then we can rearrange this equation to a system of equations, an additional system of equations, in which at the left-hand side of this equation, we have the original degrees of freedom, which are 7, the components are 7. And on the right-hand side, we have a matrix, which is called the constraint matrix, multiplied by reduced degrees of freedom. Here, this vector only has 6 components. The next step is plugging this equation, this system of equation, into the original one. And then, but by doing that, we are explicitly eliminating U5, which was the slave node, but its effect is there embedded in the equation. And then we multiply both sides of this equation to the transpose of T. This ends up to a reduced system of equation, which has only 6 components instead of 7. And the coefficient here, the stiffness matrix here, is positive definite if the original matrix is positive definite. Well, this system of equation ensures continuity. We have the same concept for 2D and 3D elements. For example, in this mesh, we have E1 and E2. E1 is nonlinear, E2 is linear. E2 only has 3 nodes, node number 2, 3, and 7, but node 5 is only part of E1. In order to capture the constant equation corresponding to this node, which is a slave node, we can use the shape functions of the lower order element. And if this node is located in the middle of the edge, shape functions give us like the value of 0.5. Then we can again construct a additional system of equation and plug it into the original one and capture, and then multiplying the resultant to the transpose of this matrix here, T matrix, then it will end up to a reduced form of system of equation, which is equal to k hat times u hat equals f hat. And k hat is nothing but T transpose times original k times T. This mathematical equation reduces the order of k and gives us k hat, which is a reduced stiffness matrix, and f hat equals T transpose times f. This concept, as I said, is applied to all the elements that we have in RS3, 3D solid elements, liners, joints, structural elements, and it works with all the simulation types that we have: static, dynamic, groundwater, consolidation. And the concept is, as I said, I just try to briefly talk about that, but we have some detailed explanation in our theory manual. Well, this brings us to the QA section, and I'm going to ask Sina, if you please, can you please check if you have any questions?
Yes, we have one question asking what is the number of DOFs?
What is the number of DOFs? It depends on the type of simulation. If it's only static, number of DOFs is 3 times of the number of nodes. But if it is a consolidation problem, it's 4 times the number of nodes because we have pressure as well.
Okay. And also for solid, we have, for each node, we are having 3 degrees of freedom,
yes.
Displacement in X, Y, and Z. Let's just add this comment as well. I think you answered this one during your presentation, but someone asked us, does hybrid mesh work with consolidation?
Yes, hybrid mesh works with all simulation types that we have: consolidation, groundwater, dynamic, and static.
Yes. And the last question we have here is, which solver is better, iterative or direct solver? So maybe
I'm going to pass it to you because we talked about the solvers.
So it depends, first of all, on the hardware you have on your computer and also the size of the model. In general, then the number of elements, maybe we say it depends on the number of active degrees of freedom in your in each stage. But in general, if number of elements is less than 2 million, and your computer letting you to do the direct solver, direct would be a faster option. But when the number of elements are huge, let's say over 8 million or 10 million, then iterative solver would behave way faster. So
awesome.
That's
thank you.
Okay.
So can we proceed?
Yeah.
Okay. Please give me a moment to change the presenter. Thank you.
Okay, so now let's continue. And here we want to go over 2 demos. The first one is focusing on application of hybrid mesh in slope stability analysis. So let me open RS3. Okay. So this is the model that I want to show you. So as you can see, we have an open pit, and we want to find the factor of safety of that. First, I'm going to run it with 4 noded elements, and then I'm gonna apply hybrid zone to that and compare the results. So to do the SSR simulation to find the factor of safety, you can go to the project setting, shear strength reduction, and activate the analysis. I already applied the boundary condition, And if you go to the mesh tab, you can see the applied mesh. So here we have 4 noded elements. So you can see it on the visibility tree as well. We have less than 300,000 elements. So I computed it. Let me open the results because it's going to take a few minutes. Okay. So here you can see the critical SRF that was calculated with the 4 noded simulation, 4 noded elements is 1.79. So let me switch the data type to total displacement. And let me go show the results when SRF is 1.82. So after we have the failure, so you can see which area of the slope is going to be like a slide. And if you want to see it better, I'm gonna turn off the exterior contour to see the results on the contour plane. And here it's clear that the mode of the failure is shear. Okay, now let me go back to the original model we had, and this time let's apply the hybrid mesh. So first step, I'm going to delete the current mesh we have. Now I'm going to go to the mesh menu, define higher order region, and now I can locate the this higher order zone in the model. So I'm going to assign it around the area that was captured with the 4 noded elements. I'm just going to reduce it slightly. Okay. Perfect. That's excellent. And now I click OK. Second step was to go into the mesh setting and change the element type. So now we have the third option. So I'm going to pick mixed 4 noded and 10 noded. When you switch the element type, you can see the list of active higher order regions you have. You are not limited to only have one. You can define as many as you want. And then you can click mesh. So now the program is going to create the mesh for us. What we expect to see is to get the same number of elements as we had for 4 noded, but any element inside of the box would be 10 noded, and anything outside of it would be 4 noded. Okay, so you can see I'm getting exactly the same number of elements. Again, that's all we needed to do, and you can just go to the compute and rerun the model. I already have the results, so it's in the hybrid. Okay. And let me go to the results tab. Here, the critical SRF is now 1.61 instead of 1.79 that we had with 4 node. So it's like 14–15% drop in the SRF. Now let me switch the data type to total displacement. And go maybe 2 iterations after the critical one to see the shape of the failure. You can see now we are capturing a larger zone in compare with 4 noded. And if I turn off the exterior contour, you can see the failure is more localized around the surface. Yeah. To know if our calculation is correct or not, I repeated the same analysis, this time with 10 noded. So let me go back to the slides to do the comparison. Okay, so with 4 noded, critical SRF was 1.79. In hybrid and also 10 noded, I'm getting exactly same number, 1.61. But now let's compare the calculation time. 4 noded, as we expect, is going to be the fastest one because we are having less degrees of freedom. It took 17 minutes. Hybrid took us less than half an hour, but 10 noded is taking 5 times more than what we had when we had hybrid mesh. So you can see by using same number of elements and assigning hybrid zone to the model, I can get the same results as 10 noded, but at least 5 times faster in this example. This is the power of hybrid mesh. We expanded our comparison also with the slide 3. So we used the intelligent search in a slide 3 that was recently released. Slide 3 also calculating the factor of safety is 1.61. So it is exactly the same as what we calculated with finite element. And also the failure area is captured very close to what we calculated with the hybrid mesh. Now let's see what we get if we increase the mesh density for the 4 noded elements, if we increase the density of the element at the area that we had hybrid mesh. So in the images, you can see where we are increasing the density of the elements. So 3 more cases, we define these 3 additional cases. We double the number of elements to 656K, less than 1 million, and 1.82 million elements. The factor of safety is reducing slightly. It's still far from slightly different from 1.61, the accurate solution, but the computational times going up like significantly. Even with 1.82 elements, it's a very dense mesh, which takes a lot of time. I'm still not getting the same result as we had with the hybrid. So to summarize what we just talked about, here since we did 6 different simulations in this table, you can see the calculated factor of safety for each of them. And here we are normalizing the time between these simulations. We normalize them all based on the coarse 4 noded mesh we had. Just by comparing the results, the calculated results, and the amount of time, you can see the hybrid mesh is the way to go. You can get accurate results with a way faster simulation. That's why we introduced it in RS3. Now let's go and talk about the application of hybrid mesh in tunneling to see if it has any effect in linear results and how it works. So let me open another model that I had. Okay. So I defined, so we have that we are doing the tunneling in this geometry. It has multiple layers of soil. We have clay, silt, and sand. And I have defined all these layers using the borehole manager. So it was very straightforward to create the model. Also for the tunneling, I use tunnel designer. So after each excavation, I'm assigning the liner around the tunnel. So if I go through all the stages, you can see where the liners are assigned. Okay, again, let me open the results. Okay, this is the results when we had 4 noded elements. Here we are interested to find the bending moment around y-axis, and also we want to find the circumferential forces at in a specific section. Let's say 20 meters away from the tunnel face. To see the linear results, actually maybe it's a good idea to, before we check the linear result, let's see the yielded zone around the tunnel. So to do that, I'm going to go pick yielded element, activate solid and tension, shear and tension. And if I go to the last stage, you can see the most of the failure is in shear just around the tunnel. Now let's go to the liner results. And I'm gonna turn off the yielded elements. Okay, so by default, we are seeing displacement in X. Now let me switch that to a moment about Y-axis. And in order to find the moment distribution around at a specific section, I need to define a query line there. So what I'm gonna do, first let me hide the soil layers. I'm gonna define a cutting plane in XZ, and I'm gonna locate it 20 meters away from the tunnel. So it's gonna be minus 15. And I click OK. Now I'm gonna pick the liner which is in that section. I'm gonna pick the plane that I just defined, and I go to interpret, queries, add liner line, query at intersection. And then I define number of points I would like to see on the query line. So the query line is created for me. So if I select that, and then I can ask program to graph data for me. And we can see the moment. Let's go back to the model. And this time, if we want to find the circumferential forces, using the global coordinate is not going to help me, because it's just going to tell me the axial forces in X, Y, and Z. I need to define the liner coordinate for the tunnel. So how can we do that? Let me hide one of the results here. So I'm gonna go to surface selection mode, hold Shift key, and select the area around the tunnel. Then I go to support, liner, define liner local coordinate for tunnel. And the tunnel direction is in Y-axis, which is the program could find it automatically. I click OK. And now you can see these local coordinates are generated for me. So X, local X is the red color, Y is the green color, and Z is the blue one. Now I can switch the the coordinate. So I'm going to switch it to tunnel frame. This is the one we just defined. And you can see the results of the moment didn't change because the y-axis of the local and the global coordinates are the same. But if I switch it to, let's say, axial forces in X, now the results are different. Now I can ask program to plot the data for me. So graph data, and there you go. We have the circumferential forces around the tunnel, which is not very clean. As you can see, it's not smooth enough. What will happen if we repeat the same thing, but this time adding the hybrid zone? So let me go back to that the second model I made, so you can see where the hybrid zone is located. I'm going to go back to the results, switch the data type to liner. Okay. So here I also defined all those tunnel frame and the cutting plane. So I'm going to pick the go to the last stage, pick the query line, and ask the program to plot axial forces in X and graph data. Now you can see results are very clean and smooth. So using hybrid mesh can also improve the results on the liner as well. Let me go back to the presentation. Okay, so here I have a few results that I compared between 4-node and hybrid. First of all was the yielded area. Of course, whenever we are using higher order elements, I expect to capture more failure around the tunnel, which is obvious here for us. The second one is comparison of the curves that I just plotted. So moment and circumferential forces. At some points, the results of 4-noded can be like 30% off from the correct value that we are getting from 10-noded and hybrid. Same thing also for the loading. I repeated the same process again, increasing the density of the mesh, as you can see around the tunnel. So from 33,000 to 137,000 elements to see if it's going to improve the results of the 4-noded. For the moment, the results didn't really change much, but for the circumferential load, the results are getting a little bit closer to the hybrid mesh, but it's not still close enough with the accurate results we got from hybrid. So just to summary of what we talked about, for whenever you are doing analysis like underground excavation, you have tunneling, you have stoping. If you have open pit, you want to find a slope stability, feel free to use the feature that we developed. As you saw, it gives you accurate results and you can save a lot of time. Beside the hybrid mesh, I also wanted to cover one additional thing that we released with RS3 in the previous release. So let me go back to here. Okay, I'm going to close this one. So I wanted to show you the feature that we updated, which is the deform configuration. Let's say you are interested to see the deformation of the liner after you are applying the load, how we can do it. So let me pick one of the liners. I hide everything. Let's keep this one. So you need to select the liner, then you go to interpret. You can pick show deform configuration. So I'm going to click on that, and now here you can see the deformed and undeformed shape of the liner. If you select that, you can you have a control on changing the scale factor. You can change it to any number that you want to exaggerate it more to make it more obvious if it's not clear. Beside that, if I switch the data type to the solids, and I activate the layers. Okay. If you don't select anything and ask the program to show you the deform configuration, it automatically shows that for all the external boundary. So I'm not going to select anything. Click on deform configuration. And now you can see the deformation. So I think it's very clear that how the tunnel is deformed. Let me here change the scale to different number like 2. So it's going to update it. Now it's more obvious how the geometry is changing. So I just wanted to use this opportunity to show you about the feature that we added to the program. All right. So let's conclude here. If you are interested to know more about the hybrid mesh, as Arsalan also mentioned, we have a great documentation about how to use the hybrid mesh in your model and how the engine is handling that with more detail, more than what you just saw today in the webinar.